Hi, this is Group 7's presentation on turbo machines. A turbo machine is classified as any mechanical system that has blades attached to a rotor with a fluid running through it. So you can either input energy to move the fluid like a pump, or you can have an already moving fluid and have it output energy through a turbine. And they are classified upon the direction of fluid motion. So the governing physics of a turbo machine is the following. The absolute velocity of the fluid is equal to the relative velocity of the fluid with respect to the blade fans plus the blade velocity. And if you have the specifications of your system, like the radius, you can calculate the shaft work done by multiplying the torque of the shaft times the angular momentum.
Okay, next we have flow classifications. Turbo machines can fall under three categories based off their type of flow. Axial flow, which utilizes an axial flow component from the inlet to the outlet of the rotor. Radial flow consists of a radial flow component at the rotor inlet and or outlet. And mixed flow, which involves the usage of both radial and axial flow components. Flow classification becomes important when we try to classify pumps, because different flow types interact more efficiently with different head and flow rate specifications. For example, radial flow pumps operate efficiently in scenarios with high heads and low flow rates, such as in the centrifugal pump, filter systems, and cooling systems, while axial flow pumps operate efficiently at high flow rates and low heads, such as in irrigation systems, drainage systems, and propeller pumps. Mixed flow pumps come into play when both axial and radial flow components are required.
The centrifugal pump is one of the most common radial flow turbo machines. The main components include the impeller, which is attached to a rotating shaft, and a stationary casing enclosing the impeller. As the impeller rotates, fluid is sucked through the eye of the casing and flows radially outward. As the blades rotate, energy is added to the fluid, and both pressure and absolute velocity increase as the fluid flows from the eye to the periphery of the blades. Pump scaling laws include dimensionless parameters and similarity laws that relate experimentally determined pump characteristics to geometrically similar pumps. The most important dimensionless parameters include the head coefficient, the power coefficient, and efficiency. These dimensionless parameters are a function only of the flow coefficient and therefore provide desired similarity relationships for two pumps operating at the same value of flow coefficient. In special cases, pump operation speed and impeller diameter effects on pump characteristics are taken into consideration. Specific speed may be used to decide what general pump geometry to use for maximum efficiency, and suction-specific speed is useful for determining the required operating conditions on the suction side of the pump. Now, let's take a look at turbines.
Next up, we have turbines. Turbines are built to extract energy from fluids as they flow and rotate the essential rotor, creating torque. We can classify these turbines into either impulse or reaction turbines, kind of like the different flow types for pumps. Impulse turbines get their energy to the rotor by the fluid turning and moving the blades. These turbines are useful in cases where you have a large head and low flow rate. An example of this would be a hydroelectric dam, where the water source is located above the turbine. Meanwhile, we have reaction turbines, where they utilize the turning of the fluid and its acceleration to move the blades in the rotor. This is why reaction turbines are better to use in situations where there are high flow rates and low heads. An example of this would just be wind turbines, where the wind is on the same level as the turbine.